Real gases are not ideal. Have a look at this example we have checked before. Pay attention to the product of pressure and volume at high pressure. It is no longer a constant. The PV of helium increases with pressure. The PV of methane and ammonia decrease with pressure. The deviation from Boyle's law is caused by the interaction between particles in real gases. In helium, repulsion is the main interaction between particles when they approach each other. We know that particles actually have their volumes, that is, the sizes of their electron clouds. When the electron clouds of particles overlap each other, they interact. If the orbitals of the particles are full, the new orbitals from the interaction of the particle orbitals should have higher total energy than the particle orbitals. Thus, the particles repulse each other. This phenomenon can be understood as the effect of Pauli exclusion principle. We can incorporate the volume of particles into the state equation of gas. Due to the volume of particles, the space in which molecules move freely is reduced. Thus, the volume in ideal gas law is replaced by the volume of the container subtracted by the volume of the gas particles. Here, N is the amount of gas. B is the volume per amount of gas. In methane and ammonia gases, attraction due to van der Waals forces is the main interaction between particles when they approach each other. The strength of attraction depends on the type and mean distance between the particles. Between polar molecules such as ammonia, the Keesom interaction is relatively strong. In comparison, between spherically symmetric atoms such as helium, the London dispersion force is very weak. Before the particles collide the wall, they experience drag from the particles behind them. They are slowed down, so the pressure to the wall is reduced. The drag to one particle is proportional to the particle density. The number of particles colliding the wall is also proportional to the particle density. So, the decrease of pressure is proportional to the square of the particle density. Here, A is the strength of attraction between particles, which depends on the type of them. A real gas has both repulsion and attraction between its particles. The state equation of gas considering the effects of both repulsion and attraction in the forms introduced previously is known as the van der Waals equation. By fitting the real behavior of a gas against the van der Waals equation, we can calculate the values of A and B. The significance of van der Waals equation is that it makes it possible to calculate the microscopic properties of particles, such as their sizes and attraction, by measuring the macroscopic properties such as pressure, volume and temperature. The shape of PV curve with van der Waals equation of a certain gas changes with temperature. It qualitatively explains the mechanism of phase transition between gas and condensed phases. We will discuss it in a later chapter.